In this video, I introduce a temporal difference for learning world predictive control. Reinforcement learning learns a policy pi to maximize the reward by iteratively interacting with the stochastic environment. I show in this equation and in this figure, this agent, this action, this environment, this reward, and this state at time t. Where theta is a model parameters, and Q theta is a state action value function. However, the model predictive control is a trajectory optimization process as shown here, which obtains a local solution to the trajectory optimization problem by estimating optimal actions from AT to AT plus H over finite horizon H and executing the first action AT as shown here. The solution is found by iteratively fitting mean and covariance of a Gaussian distribution with a diagonal covariance over a finite horizon H using the derivative-free cross-entropy method and sampling trajectories generated by a learned model. TD-MPC combines MPC with a task-oriented latent dynamics model and terminal value function jointly learned using TD learning in an online reinforcement learning setting. TD-MPC leverages the model predictive path interval control for planning, learned latent dynamics, D state, real-world signal, R state, or terminal state, action value, Q state, and a policy pi state that gets planning, as shown here. And this is the description of a TD-MPC model, where Z t plus 1 calculated from D state AT sampled from a normal distribution at iteration J minus 1. The top key returns phi are selected to obtain new parameters mu sigma at iteration J from these two equations. TOLD model is jointly learned together with the terminal value function using TD learning. During inference, the TD-MPC leverages the learned TOLD model for trajectory optimization, estimating short-term rewards using the model rollouts and long-term returns using the terminal value function. The TOLD consists of 5 learned components, namely representation function, H theta, latent dynamics function, D theta, real-world function, R theta, value function, Q theta, and the policy function, pi theta, as shown here. This image, this latent embeddings, this value, this reward, and this action, this latent dynamics. The training objective is to minimize NG as shown here, where Zappa is a trajectory, ST, AT, RT, ST plus 1, sampled from Ripley buffer, and lambda is a future discount factor. The single-step loss L is computed by using this equation, which consists of 3 terms, namely real-world prediction loss, value prediction loss, and latent state consistency, which is used to jointly optimize for real-world prediction, value prediction, and latent state consistency loss that regularizes the learned representation. All the predictions are performed in the latent space. The exponential average moving theta bar of the online network parameters theta is used to update the value target network. The TD objective requires estimating the value here, which is obtained by learning a policy pi, as shown here. This is the description of TOLD model. For more details, please check with these references. Thank you. Bye.